Hello, everyone. First, I would like to thank the organizer to allow me to present this work. So I'm Nicolas Aymar. I'm a PhD student of the Paris Observatory under the supervision of Frédéric Vincent and Thibaut Pomar. And I will present you the result of my work on modeling the flares of Sagittarius A star observed by gravity, a work that I've done with Anton Dmitriev and Andreas Zek. So first, let's introduce a bit of the subject. So when we are looking at the galactic center in radio, we can see there is a bright source called Sagittarius A. And when we are looking at this specific region, but this time in near infrared, we can see there is a lot of bright stars which has an orbital motion around the same object with a mass of 4.3 million solar masses. This source called Sagittarius A star is very faint and is thus the closest supermassive black hole candidate to Earth, which has been confirmed by the Nobel Prize in 2020 to Andreas Genzel and Andreas Ghez. So these sources, Sagittarius A star, has been observed for more than 2 decades. And here you can see a spectrum of the quiescence spectrum of this source, which comes from radio to X-rays. And in addition to this quiescent state, we also have observed bright episodic emission here in near infrared, what we called, in fact, flares. And these flares can have a very high variability from 20 minutes to approximately 2 hours. So this observation has led to the creation of the gravity instrument, which is installed at the VLTI. And in 2018, Gravity observed 3 bright flares, which shows an orbital motion. So they use a simple hotspot model to fit the orbit, but do not fit the light curves. In addition, Gravity has observed that these orbits has a super Keplerian velocity, and that the center of these orbits has a slight offset with the position of the black hole. So this is what I worked on and tried to model. So astrometric data, the light, but also the light curve, and try to find a model which is able to explain the super Keplerian velocity and the offsets with the position of the black hole. And for that, I built a physically motivated model based on magnetic reconnection. Indeed, GeoMHD and GeoPeak simulations showed that black hole magnetosphere generates current sheets which led to magnetic reconnection. And thus, ambient plasma, and in our case, we will focus on electrons, will fall in X points where there will be accelerated to very high Lorentz factor. And these accelerated electrons are then trapped into small plasmoids. We can merge all together to form a magnetic flux tube that you can see here. And this flux tube can have 2 specific magnetic field configuration. It could be helical magnetic field or vertical magnetic field. However, in our case, for the moment, we do not consider any specific magnetic field configuration and consider tangled magnetic field. So we followed the results of the GeoPeak peak simulation results of Elmela et al., which are resumed in this sketch. So we have, in that case, they have 3 magnetic field lines. The open field lines, which are anchored to event horizon and goes to infinity, the one which are anchored into the disk and also goes to infinity, but with a different polarity. And finally, we have closed magnetic field lines. And among them, there is one magnetic field line which is of particular interest, which is called the separatrix. And it is at the Y point here of this separatrix where the current sheets form, and that we will have reconnection. So instead of modeling all the small plasmoids generated by the reconnection, in fact, what we model is a single large plasmoid, which will be the results of the merger of all of the other small plasmoid. And the small plasmoid will feed this big sphere of plasma, this big plasmoid with freshly accelerated electrons. Another aspect of another result of El-Mella et al. Is that the separatrix has a particular azimuthal velocity. Indeed, its velocity is the Keplerian velocity at its foot point. However, as you can see here, by comparing the two cylindrical radius here, the one of our plasmoid is way larger than the one of the foot point of the separatrix. And as the foot point is at a lower radius and a Keplerian velocity, so this means that in our point of view, the apparent azimuthal velocity of our plasmoid, which is the same as the velocity of the footprint of the separatrix, will appear as a super Keplerian. So this is one explanation for the super Keplerian velocity observed by gravity in 2018. Moreover, this foot point, so the position of this foot point in the disk, depends on the spin. This is also the result of El-Mella et al. Work. And so if we assume that we have a circular orbital radius of around 10 rg, we can have a constraint on what should be the orbital velocity of our plasmoid. And so by making a measurement, we can have, and I would want to be very, very careful with that, we can have an indirect estimation of Sagittarius A star spin. However, it is very model dependent and more work are needed to be clear about that. But I think it's an interesting result for the future and for the measuring the spin in the future. Okay, so that was the general results of El-Mella et al. Paper on which I base my work. But what we are modeling, what is our final model? So here you have a sketch where we consider a jet for the and a torus for the quiescent state, and in fact, it's the quiescent state, as you will see just after, has an importance, and our plasmoid, which is ejected in the magnetosphere in an helical motion. And for the evolution of our plasmoid, we decided to make a kinetic approach to follow the distribution of electrons. This approach is divided into two phases, a growth phase where we inject accelerated particle in our large plasmoid, and these electrons follow a kappa distribution. So a thermal core with a power law tail to account for non-thermal electrons. So this mimics the merge of the small plasmoid into our big one, which gives new freshly accelerated particles. And after the injection, so the growth is over, when there is no more merger, we enter into the cooling phase where all the electrons, there is no more heating process, and they are only cooling down through synchrotron radiation. However, all these aspects are intrinsic evolution, and in addition to that, there are effects that needs to be taken into account to have our final observed astrometry and light curve. So the first important effect is a beaming effect. So you probably know about this effect when a particle emits radiation and has a very high Lorentz factor. This radiation will be focalized into the direction of propagation. So we talk about positive beaming when the particles goes toward us, and negative beaming when it is going in the opposite direction. And the second important effect is the influence of the jet. In fact, the quiescent state, we tested that different scenario for the quiescent state, but here we just simplify with a jet. So include the quiescent state as an importance. And all these two important effects are are visible in this figure. So let's first talk about the beaming by looking at the light curve. So you can see in dash gray the intrinsic light curve, and the four full line curves correspond to half an orbit around the black hole. So different phases of the beaming modulation. And the green one corresponds to
You're not yet connected. No, we can't hear you.
Okay, can you hear me now?
Yes, that's okay now. Yep.
Sorry, sorry about that. Yeah, so the green line corresponds to a synchronized positive beaming with our intrinsic light curve, which is more simpler than what I presented before. It is here a very Gaussian time modulation, just to have a simple cases. And in the blue one, thank you. The blue one corresponds to opposite phase between intrinsic emission and the beaming modulation. So as you can see, it has the beaming has a strong influence on the observed light curve compared to the intrinsic one. Now let's talk about the influence of the jet. It is very, for light curve, it is quite obvious. When we had a constant flux, it will just make an offset for the light curve. But for the astrometry, it is way more complex. Indeed, what in that case, what we have is that the flux at the beginning and the end of the observing time is dominated by the jet and so the quiescent state. So the astrometric data, so the centroid flux of the whole image will be close to the centroid of the jet. And as the flare, the flux from the flare increase and start to dominate the flux of the whole image, the astrometry will follow the flare in its orbit before returning back to the centroid position of the quiescent state, because the flux from the flares is negligible compared to the jet. So in fact, this just adding the jet instead of having a full circle centered to the position of the black hole, just because we have this flux ratio between the jet and so the quiescent and the flare, just be adding this quiescent state makes the strong offset between the center of the apparent orbit and the position of the black hole. However, here it is quite extreme cases because at the beginning and the end of the flare, the flux is dominated by the jet, but in reality, with gravity, when we observe a flare, it is already the flux from the flare is already high, and it will be not as much as you can see here, but it is still non-negligible. So now I will present you the results. So it is not the result of a fit, but just trying to find a set of parameters which shows good agreement, and it is quite satisfying. And the one important aspect is that the orbital velocity that we need to explain the data is fully compatible with the constraint that I presented you before from Elmela et al. Paper. So this is a strong argument for this scenario. Moreover, as you can see, by looking at the light curve, comparing the intrinsic and observed one, you can see that there is indeed a strong influence of the beaming effect. But in general, this model shows very good agreement with the data. So we are quite happy, but now what will be the next steps? Obviously, it will be to make a real fit of the flare data, not only for gravity data, but for all infrared data, but also studies of polarization, because gravity is also able to measure and has measured polarization loops for the flares. And more recently, ALMA has also measured the polarization loop for the flares, but I will let Maciek talk about a bit more in details about that. But this, taking into account the polarization, can help us to have a diagnostic of the magnetic field configuration. And another important aspect is the multi-wavelength analysis, because these flares are not only visible in infrared, but also in X-rays and submillimeter. But all the infrared flares are not visible in X-rays, and there is possibly a time lag with the submillimeter band. So different features that we need to be explained, and that to be explained by a single model. So this will be the next step to to explain all of that. So to conclude, I will say that gravity, so has observed that flares at an orbital motion around the supermassive black hole with a super Keplerian velocity and an offset. And adding the quiescent state naturally explains this offset. And we build a model based on the GRMHD and GRPeak results of magnetic reconnection, which is very promising. And the next step will be to feed the data, study the polarization, and make a multi-wavelength analysis. Thank you for your attention.